Hey everybody, what we're going to do today is solve an initial value problem, but we're going to do it using Laplace transforms, right? So this is something that you typically will do at the beginning of a controls class. You'll learn this, and it's pretty straightforward, but a lot of the times students kind of miss some of the steps, and so they end up missing the problem. So I figured we'd go over this example to kind of walk you through the different steps. So what we've got here is a differential equation. Remember in this case when we have the little dots, that just basically tells you it's the order of the derivative with respect to time. So like x double dot would be the second derivative of x with respect to time. X dot would be the first derivative of x with respect to dot. Or not with respect to dot, with respect to time, right? So that's what the dot means in case you haven't seen that before. So we've got this expression here on the right side. We've got 4t minus 6. And then we've got our initial conditions, right? So I've got x at t equals 0 equals 1, and then x dot at t equals 0 equals 3. So just to kind of visualize this, you can think of x as being like displacement. X dot would then be like a velocity, right? So this is giving your initial displacement, your initial velocity, all right? So that's kind of what those are. And what we're looking for in the end is an equation that is x of t equals something. All right, so that's what we're going to get when we solve this initial value problem. All right, we're going to get x of t equals an expression. That's what we're looking for. And if we get it correctly, or get it correct, we should be able to plug in t equals 0 and get 1. All right. Okay, so let's go ahead and walk through our steps here. So I want to use Laplace transforms to solve this. So remember, for Laplace transforms, let's write this down. If I've got the first derivative of a function, so f dot, right? Then if I take the Laplace of that, then what I'm going to have is s times the Laplace of the function f of t minus f at t equals 0. Okay, so f here is just a generic thing for a function, right? And we can write this in the simplified notation, and instead of putting the little Laplace operator, we can put s times capital F of s, and then minus f at t equals 0. All right, so anytime we see this capital letter here like this, that means we've taken the Laplace transform of the function. So here we took the Laplace transform of f of t, that gave us capital F of s. All right. This one here didn't change because we're just taking our function f of t, plugging in t equals 0. Okay, so that's what we get when we're taking the Laplace transform of the first derivative of f. Now we have something similar for the second derivative. So if I take the Laplace of the second derivative of f of t, I'm going to have s squared times the Laplace of the function f of t minus s times f at t equals 0 minus f dot at t equals 0. All right, so this would be like our first derivative of f when t is 0. And then if I rewrite it using this capital notation, we could say that that's equal to s squared f of s minus s times f at t equals 0 minus f dot t equals 0. All right, so these are just equations for Laplace transforms. All right, so those work for any problem, not just this one. So now let's apply these to the situation I have right here. So what we want to do when we're doing an initial value problem is we want to go through and I want to take the Laplace transform of each of these terms in this equation. All right, so we want to do the Laplace of all of these terms. That's what we're going to do first. All right, so let's draw a little arrow here. So we're going to do the Laplace of x double dot minus 3 times the Laplace of x dot. When we got a constant, we can just pull it out here. And then we're going to have plus 2 times the Laplace of x. Whoops. And then that'll equal basically the Laplace of 4t. And then minus the Laplace of 6. All right. And again, you could have pulled out that 4 there if you wanted. I just left it in there. Okay, so now that we've got that, let's go ahead and see what we've got here. I'm doing the Laplace transform of x double dot. Okay, well look up here. This is the same thing, right? I just have x instead of f. Otherwise it's the same. So I'm going to use this expression here in place of this. Okay? Only difference is instead of f, like we have here, we're going to use x. Okay, so we're going to have s squared times capital X of s minus s times x at t equals 0 minus x dot at t equals 0. Okay, so that right there takes care of this term. Now we move to the next term. So now I'm going to have minus 3 times the Laplace of x dot. Well, the Laplace of x dot is going to use an equation like this, right? So instead of putting f, though, we're going to put s. So we're going to have minus 3 times s x of s minus x at t equals 0. So this right here takes care of this term. Now we go to the next one. So this is just plus 2 times the Laplace of x. Well, the Laplace of x is just going to be capital X of s. So now we've got plus 2 capital X of s. And then over here on this right side, this one looks a little bit different, right? We've got t's in here. For that, you're going to need a Laplace transform table. So this is the one that I always use. I think it's from the Ogata book. I copied this thing many years ago. And what we're going to do is we're going to look up what our function looks like, and then look to the right. That gives us the Laplace of that function. So if we look here, I've got 4t. All right. So if we go right here to entry 3, this is t. The Laplace of that is 1 over s squared. And remember, I've got the 4 in here. So we're going to have 4 over s squared on the right. And then on this one, we've got just a 6. So that's going to be a number. Anytime it's just a constant number, we're going to use this unit step input. All right. So if we've got a unit step, we're going to have 1 over s. Ours is multiplied by 6, though. So we're going to have minus 6 over s. Okay. So we just did the Laplace transform of those 5 terms. That's all we did. Okay, the ones on the right side, though, we needed to use the Laplace transform table. So let's put a note here. All right, so now what do y'all think we should do? Well, I'm thinking we can get rid of some of this, because if you look, I'm given this information right here, right? I know x at t equals 0 is 1 and x dot at t equals 0 is 3. So I can use these values down here in my equation, right? And then that'll help us simplify it a little bit. So x at t equals 0 here, we can set that to 1. X dot at t equals 0 goes to 3. And then this one right here goes to 1. Right, so that will give us some values and get rid of some of these x terms. And then what we want to do is kind of simplify this. So notice I've got 3 of the capital X terms, and then I've got this s term here. So we want to kind of group up our terms. So if we do that, we're going to have s squared minus 3s plus 2. That is my phone being very loud, times x of s. Okay, so here's the first term right here. Here's that second one. And then here's that third one. And then we need to group up these last terms here. So I'm going to have minus s from right here. And then we've got minus 3 plus 3. All right, so I'll write them out, but those are going to cancel. So those two go away. And then right side stays the same because we didn't change anything over here. Okay, so now I've got that. So it's a little bit simplified. Now what I'm trying to do is I want x of t. That's what we're looking for. So this is our final goal, is to find x of t. I want to know what expression that equals. So in order to get that, I need to get x of s by itself. And you'll see why in just a minute. So I need to move this little s over here to the right. Okay, I want to move it over, and then eventually we'll be able to solve for just x of s. Okay, so we got s squared minus 3s plus 2 times x of s, and then that's going to equal 4 over s squared minus 6 over s plus s. Okay. Now, a lot of times people will see all these fractions, and people don't like fractions, right? It kind of makes them get panicked that it's going to be a lot of work, a lot of algebra, but it's not that bad. So what we want to do is let's get a common denominator over here, and then we'll move forward after that. Okay, so let's rewrite the left side. That didn't change. Common denominator here could be s squared. So if that is our common denominator, I'm going to have 4 minus 6s plus s cubed over s squared. All right, so all we did, common denominator. Now, let's go ahead and solve for x of s. Okay, so all we need to do is divide through by that polynomial there. So we got the numerator here. We got s squared in the bottom, and then we're also going to have the s squared minus 3s plus 2 in the bottom. Okay. Now at this point you've got all these polynomials, and this is where students can get confused because you have to kind of factor this out, simplify a little bit. So the easiest thing to do if you have a graphing calculator is to use the graphing calculator to factor all this out. Otherwise you kind of have to kind of play around with it. But if you want to factor this out, this top polynomial can be rewritten as s minus 2 times s squared plus 2s minus 2. And then in the bottom, we got s squared. And then this polynomial right here can be rewritten as s minus 2 times s minus 1. Right. And again, I usually use the graphing calculator to do this. So if it has an algebra menu, it'll give you the option to do that, and that makes it a little bit easier. Okay, so now these two will cancel. All right, so that's good. And let's see what we should do next. Let me rewrite this first. All right, so we got our s squared plus 2s minus 2 up top, and then we got s squared times s minus 1 in the denominator. All right, so now if you notice, we've got this complicated fraction here. It's got polynomials on top and bottom. What we want to do now is use partial fraction expansion. Okay. Now, hopefully you remember partial fraction expansion from calculus, but what we're going to do is we're going to set this equal to a fraction that is a over s squared. So that's for this term here. Now, since this is squared, I'm also going to put another fraction where we have plus b over s. All right, so that takes care, these two here take care of this one term. And then finally, we're going to have plus c over s minus 1. Okay, I tried to focus that in a little bit. Kept going out of focus. Okay, so now we've got this. So what we want to do now is basically find these constants a, b, c. So remember, this is partial fraction expansion. And the goal of partial fraction expansion is to reduce this complicated fraction down into a sum of simpler fractions, right? Because then these are easier to look up in the Laplace transform table. So that's the goal here. So we need to find a, b, and c. All right, and the way we're going to do this is just by kind of looking at the numerators here. So we got s squared plus 2s minus 2. And then over here, you're going to look at basically the common denominator. So common denominator would be s squared times s minus 1. So for this fraction here, we would have a times s minus 1. For this one, we'd have plus bs times s minus 1. And then over here, we'd have plus c times s squared. Now, how many equations am I going to need to solve for these three unknowns? I need 3 equations, right? So 3 equations, 3 unknowns. So what we're going to do is we're going to plug in different values for S to get our different equations. All right, now, obviously, if you can make these terms here go to 0, it's going to save you some time. So first of all, I'm going to put in S equals 1. All right, so let's plug in S equals 1 everywhere we see S. So that's going to give me 1 plus 2 minus 2 on the left. And then that'll equal A times 1 minus 1, so that goes to 0, plus B times 1 minus 1 goes to 0, plus C times 1 squared. So now with this, we get one equation, one unknown, right? C is the unknown, so I can solve for C. And C is going to be 1. Okay. Now we do the same thing, except for let's use a different value of S. So let's use S equals 0, because this one would go to 0 if S is equal to 0. So everywhere we have S in here in this equation, we're going to plug in 0. So I get 0 squared plus 0 minus 2 equals A times 0 minus 1 plus B times 0 minus 1, so that whole thing goes away, plus C times 0. So this leaves us with one equation, one unknown. Now we can solve for A. Right, so if you solve this for A, we have negative 2 equals negative A, so A is going to be positive 2. And then last equation, you can just pick a random value of S. We've used all the easy ones, so I just used S equals 2. Doesn't really matter what you pick here. So that's going to give me 2 squared plus 2 times 2 minus 2 equals A times 2 minus 1 plus B times 2 minus 1 plus C times 2 squared. Now with that, I already know what A and C are, right? So we can plug in those values. So A will go to 2, C will go to 1. And then the only unknown ends up being B. All right, so this will end up being 6. And then you've got this right side, so then solve for B. And you're going to get B is 0. Okay, so now we've finished the partial fraction expansion, so we're going to come back up here. We're going to plug in our A, B, and C values. And let's see what we get. So I got 2 over S squared. The B term goes away, so I'm not going to write that one. And then we're going to have plus 1 over S minus 1. All right, so this is still x of s, right? So this is still the Laplace transform of x of t. Okay, because you have that relationship right here. So what we're wanting to do is solve the initial value problem. So I want to know what x of t is. So in order to get x of t out of here, we have to use the inverse Laplace. All right, so we're going to use the inverse Laplace of x of s. And this is going to use the table. Okay, so we're going to go back to our table here. And this time, let's see if I can get this on here. We've got 2 over s squared, right? That's our first fraction. So we're going to look at these separately, right? So we got 2 over s squared. So I'm going to look in this column here on the right and find something that has that form. All right, well, look right here. I've got 1 over s squared. So that's the same form, it's just multiplied by 2, so no big deal there. So to get the inverse Laplace, we just go to the left. All right, so the inverse Laplace will be t. And since I have the 2, I'm going to have 2 times t. Okay. Now we do the same thing here. I've got 1 over s minus 1. So we look over here on this side, and if you look right here, This has the same form. Okay, so this says 1 over s plus a. Well, that's fine. We can just have an a that's a negative number, right? And then if we look over here, it's e to the negative at. All right, the negative at assumes we have a positive here. Ours is negative, so we're going to flip that sign. And that's going to give us plus e to the t. All right, and that is your x of t. So this would be the result. All right, so we took that differential equation, we used those initial conditions, and we got all the way down here, and x of t gives us the equation here that we have for our problem. So then if I were to go through and plug in x at t equals 0, I should get 1. All right, which is what we're going to get, because we'll end up, this will go to 0, this will go to 1. That checks out. And then if you wanted to double check, you could take the derivative of this with respect to time, plug in t equals 0, you should get 3. All right, which is what you'll get if you work through that. Okay, so that's what it's looking for when it wants you to solve an initial value problem. It's wanting you to get an equation that's a function of time. All right, and typically what you're going to do every time, you're going to take the Laplace of all of the terms, use the differentiation theorem to replace the terms where we have the derivatives, just like we did here. Then once you do that, you're going to replace your initial conditions with the actual values. Simplify to where you get x of s, just like we did here. Then partial fractions if you have to use them, which is all of this, and then use inverse Laplace. All right, so typically that is what you will do in a problem like this. Okay, so hopefully y'all found that helpful, and I will see you guys next time. Y'all have a great rest of the day.